And we are going live. So, welcome back to the stream. Today we'll continue the IOVoodoo project, the IO being the IO identifier. But first I have to tell that what happened in the last time. I did order some STM32F401, which, well, yes and no. On AliExpress, I've ordered from 3 different sellers and they all didn't ship. So they all don't have them. These microcontrollers, let's change screen. This one, let me see bigger. This microcontroller, which we wanted to use for the IOVoodoo. So I wasn't able to, AliExpress, there was, no, yeah, AliExpress, I bought from 3 sellers. None of the sellers shipped them. Although I bought for tip different, so shortage is happening. And I did found on Mauser, I did find some, and now I have 2 of them. I think they had 7 in stocks left or something like that. We can check. Let's switch to full screen. Full screen, Mauser, STM32F400 RC6. 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 It is RCT6. Property. Good. They still have some. They have some in stock on order. So now they have none in stock. But at the time I bought them, they had at least a couple in stock, and I was able to buy at least 2 of them. And what I also did is, because of this shortage, I wanted to see if people are taking advantage of the shortage. And I created information. I created a script which parses the websites. Doesn't use the API, it just scrapes the website of the manufacturer. Yeah, distribute your prices. And I've added a couple of parts. For example, this is the level shifter we are using. The 1.6, yeah, this part is the level shifter. And you can see that the price on Mauser, so you can see here the stock. The stock went a bit lower on DigiKey, but everyone still to have enough stocks. On Mauser, the price dramatically dropped from 75 cents to 70 cents. And you can see that on LCSC, the price is increasing from 67 cents up to 71 cents. And yeah, so this does it every 12 hours. So my script scrapes the part scrapes the website for this part every 12 hours. And this way I can see what the stock is. That's the most important, but I also can monitor the price of the thing. So I've just added the price for the components we need for the IOVoodoo. Here it didn't change a lot. There was a tiny drop, but it didn't change a lot. This part here, LCSC sometimes has it or sometimes doesn't have it. Their stock management is quite weird. I don't know how they do that. But yeah, for one this part costs normally $1 or something like that. It doesn't cost that much. Ooh, on Mauser $4 per piece. That's quite high for such a microcontroller. Just an STM32. And yeah, you see that LCSC is taking clearly advantage. I have 3 times the price, but what was most important is this chip. And there you can also see, oh, on LCSC the price dropped. This is something new, seeing the price dropping. And on DigiKey and Mauser, the price is relatively. I only put these 3 manufacturers. There could be also Farnell, there could be plenty of other manufacturers, but these are my 3 main, not manufacturers, distributors. These are my 3 main distributors. let's this. I have kind of a feedback of audio. These are my 3 main distributors. But what's most important is that for prototype, I have now 2 of them, and 2 of them is enough. So this was, yeah, this is one of the things I did. Meanwhile, and let's have a quick summary about the IOVoodoo. So the IOVoodoo, let's go back to this bench. The IOVoodoo, the purpose of the IOVoodoo is to, let me get my parts. This is really a quick summary for people who don't know about it. This is the third part. And I have 2 prototypes, these 2 things. One tries to find out or tries to test all the 16 possible channels for JTAG or SVD port. The other one tries to find out if it's an input and an output, and it's not implemented, but it's the purpose also. It tries to figure out if there is a UART port. What I wanted to do is have this cleaned, and I have this clean and create the IOVoodoo, so it's a combination of both and can do most of the things. What it can do is described here. 16. I want to scan 16 channels for JTAG, that's already implemented. SVD, that's already implemented. UART, it is kind of implemented. It's not implemented here, but it is implemented on other development board. So I just have to port the code here, do some frequency measurement, and then UART decoding. I want to test if it's an input or an output. This is what also this does. So this is the combination of those. Now, if I do something more, I wanted to add some other things, have high-speed SVD, have high-speed JTAG. For now, it's all bit banging, so it's pretty slow. It is fast enough by far for scanning, but if we want it to be faster, why not? If we wanted to use an SVD adapter, I cannot use bit banging, it's too slow. Well, too slow. It's still 500 kilohertz, but I figured it's too slow. It could go a lot faster. I also want to do SPI programming because this tool is meant for reverse engineering. And in reverse engineering, a lot of flash. Sometimes it's eMMC flash, so I also kind of want to read eMMC flash. Most of the time it's SPI flash. And in this tool, I could also try to identify the SPI flash, because when you connect to SPI flash, you can read the device identification and include in database, like I included in database for JTAG and SVD devices. So that's the IOVoodoo. So why did I choose? So in the 2 first stream, I explained what this is. We decided about the parts, and I decided to use the STM32F401 because I have lots of development boards using this thing. Like, yeah, this is the development board I was using for this thing, and it worked pretty well. This is why I decided I already have code implemented for these both things using this microcontroller, so why not just reuse the code? And to do everything I need analog multiplexers for measuring. Out of the 16 channel, I want to measure the voltage if I pull up and down. So that's one multiplexer, and then I want to use hardware SPI and UART. It means that at least for 3 line, or 4 lines, no, for UART I only need 2 lines. For SPI I need 1 line. But yeah, I wanted also hardware JTAG, and hardware JTAG needs 4 lines. So I need 4 additional analog multiplexers, so I can route any of these hardware pins which are fixed on this microcontroller. There are several pins, but they're not at arbitrary pins. So I need also 4 additional analog multiplexers. What was also important, I wanted to be able to be 1 to 8 volts to 5 volt compatible. Now this is really, we'll see later on why it is kind of a pain, but 5 volts, most of the things I do by reverse engineering is really 3 to 3 volts. It's getting rare to find 5 volts devices, but this is meant as a general purpose reverse engineering tool, and so it should not break easily. And for example, if you still have one of those Arduino, this is an old Arduino, but still enough Arduinos which use 5-volt I/O lines, for example, for UART, and you still want to scan UART. So there are still some old microcontrollers which use 5 volts. And whatever you're reverse engineering, it might use that. This is why I want 5 volt, 1.8 volts to 5 volt compatibility. And for that, I need logic level translator or voltage translator. These were the parts we're using. We need at least 2 of them. And then because there are too many pins for controlling the hardware multiplexer, 5 of them, I added shift register. This way I can quickly control the I can quickly control or send data. This is the wrong way around. No, it's the right one. I can quickly send data to the analog multiplexer and control which channel I want, all 5 of them, because you need 5 lines to control one analog multiplexer. If you have 5 of them, you need 25 lines. Microcontroller doesn't have 25 spare pins just to control the analog multiplexer. I need them from something else. This is why I needed shift register, 1 for each analog multiplexer. That makes 5 additional pins. So this is a lot of components, but still it does fit in here. I've somehow put them next to each other. It kind of fits in such a case, but it is a lot of components. And I was curious, and I wanted to think, we have 5 analog multiplexer. We could use a bit focus. I wanted to know, instead of having 5 analog multiplexer, isn't there not a multiplexer which can take the 16 channels but multiplex it to something else? Let's take our multiplexer. This is the multiplexer. So bit slow, but it should be working at this point. Come on. No cache thing. Okay. Analog multiplexer, switches, multiplexers. This is the one we have, and ours has it's a multiplexer 16:1. We have 16 channels and 1 output. Now it would be nice if we have 16 channels and multiple outputs and kind of have the 16 channels go on different outputs or on the same output. Something more like, so we can look at it, the circuit, something more like a matrix multiplexer. So I looked around, there's 1616, 16.2, and I want something like 16.4 at least. 16.5 would be better. 16.4 would be the best thing. Now let's have a look at these multiplexers. This is 16.2. Where is the 1616? 1616. This one. Obsolete. But it's a cross video multiplexer, and if we look at it, at the data sheet, Go data sheet, up 16 by 16 non-blocking. It operates not, so it is an analog multiplexer. No, it's not an analog multiplexer. I wanted to have analog multiplexer. This is digital logic. It's not the range we want. We want 1.8 volt to 5 volts. And most of the other analog multiplexer which are found they don't have a matrix. Here, switch matrix. This is what some kind of want. I want a switch matrix to decide what goes in one way and what goes the other way in the analog domain, not in the digital domain. And if it's in the digital domain, I want it to be bidirectional and compatible between 1.8 volt to 5 volts. This doesn't do it. And I didn't find a switching matrix which was able to do that. Analog matrix. Does this? I found something very similar though. Back and find analog multiplex. It was 8 to. Then there were multiple circuits. Quad 1.2. Something very this one or this one? 8 to 4, like this. Switch multiplexer, exactly. Matrix switch multiplexer, and this allow is the circuit diagram. I think this gives you the option to route any of the 4 to any of the other 4 controllers. Yeah, I think any of these 8 can these 4. Problem is, I want any of. Could I use this? 1.6 volt compatible. 8 to 4 full matrix. Ah, that's what the name is. Full matrix analog multiplexer. That's almost what I want. I want 16 to 4. I could use 2 of them actually. That could be an arts. What was the price? Okay, they are not available. They don't have any price anymore. I still want the price. Even if they're price. Switch multiplexer. This. No stock, no price available. Unit price, so yeah, no price available. Let's look at some sites. There's a price available. Because with that, I can have 2 of them in parallel. Non-stock lead time. Yes, I still have the price. Quantity quote. Okay, so you have to. It's not a usual part, but at least. Was looking at analog multiplexers. I found this matrix. It's not perfect. It was good enough, but then I remembered that I had something very similar. Find that. I remember I had something similar. This device. Try to make focus. Manual focus. That's why it was autofocus. This device. This is one of my JTAG adapters, and so multiple out voodoo.info document here. That's this one. This the JTAG lockpick. It uses an FT232. This allows you very high speed, so high speed USB high speed bit banging are really fast. You just have then to define to connect to the right pins. So very often in cheap JTAG adapters you find this chip. Now they've added this second chip on the left side here, and look, the device, it's used for 2 things. It can here, this Lattice ISP Mark 4000 series. What does it say? There's not what it says. So I wasn't aware of these devices. These are PLDs, so programmable logic devices. In this case, this is a CPLD, complex programmable logic devices, I think. And what this allows you to do is kind of like a switching matrix. You can define which pin on the output goes to which pin on the input goes to which pin on the output, and so on. And the advantage of this one is it operates from 1.4 volts to 3.6 volts, and it is 5.5 volt tolerant, but it is not 5.5 volt compatible, meaning that the input pin supports 5.5 volt and it will be recognized as a high. Now the output pin will still be at 3.3 volts maximum or 3.6 volts maximum, and you have to be sure, I think it is written somewhere, supported chips from, look in the manual, downloads, manual. The manual is quite good. I like this JK adapter. It is fast, it is compact, has a lot of features, and the manual is very good. Now, interfacing with 5-volt chips, page 7. Page 7, that's page 7. And here we see interfacing with 5-volt chips. So it only, this is why it uses the CPLD. This way it can route any pin of the FTDI to any other pin on the JTAG adapter, and you could reroute it actually. So here we have already a fixed pinout, but this CPLD is programmable. So you could actually reprogram it and have a different pinout, because this, yeah, this those targets. What you see here, this is the ARM JTAG pinout with 20 pins. There are other 20 pin pinouts. TI makes a different one. You could reprogram this CPLD right here to have your interface. So to have your corresponding to your pinout, but mostly it's being used for the 1.5 volt compatibility up to 3.6 volt. Now I don't think I've ever seen a target JTAG with 5 volts. It might exist though. I don't know. But here it says yes, that the input is 5 volt tolerance, but if you want to use it as output, you need to be sure that it uses that the high threshold is 0.4 times the target voltage, because 0.7 times V would be 3.5 volts, and that's not high enough because you have 3.3 volt output. So this is good. The manual is good because it clearly explains how it works, what the conditions are, and yep. Then it has the cable. So I recommend. Thanks. Good tool. Good documentation. So that led me to remember that there are CPLDs or PLDs in general. So CPLDs allow you to have some kind of lookup tables and macro cell for arithmetic operations. But the more general term, if you just want to interconnect devices, they are called PLD, programmable logic device. Now, I've never worked with them. Here we have programmable logic devices, and then we have complex programmable. I think these ones are pretty old. Everyone makes now programmable logic devices. We want 1.5 volt compatible, 1.8 to 5.5 volt compatible. Look at it. There are not a lot of options. Filter. There is this one. And it's even called signal matrix, so it is really meant for that. At the data sheet, only this one actually. Various forms, but it's only this one. So there are not a lot which are compatible for that. Like most of the things are really compatible up to 3.6 volts. 5 volt compatibility gets phased out, but I really want to have 5 volt compatibility for really old devices, for reverse engineering really old devices. Yeah, that's I may be strain myself, but that's the goal. So I found this thing. Oh yeah, so yeah, 1.8 volt to 5 volts, but there was something wrong with it. What was wrong? We want it to act as a level translator, so we want to have 2 VDDs. Exactly, that was the problem. So on one side you could put 1.5 volts, 1.8 volt to 5 volts. On the other side I want 3 volts. The issue is that VDD2 should be lower than VDD, and not every combination works where on one side I have 3.3 volts and on the other side I have 1.8 to 5 volts. So I cannot use this PLD or CPLD, and I didn't find any CPLD which was taking 1.8 volt to 5.5 volt on one side and was giving out 3.3 3 volts on the other side. I still needed level translators and analog multiplexers. But I remember that some microcontrollers, this is the next part, and now we'll arrive why it took a bit longer, is that some microcontrollers, I've heard about microcontrollers which have CPLDs inside or PLDs inside. For example, up this device, this is the JTagulator. This is actually what's make me start this project, because this JTagulator doesn't work for me. And the SVG finder was born out of the JTagulator not working. The JTagulator here uses a parallax propeller microcontroller. Let's have a look at parallax. Parallax propeller. But parallax propeller. That's the parallax propeller 1, so it uses the 1. The propeller 2 is pretty easy to work with it. Block diagram, data sheets, get the data sheet, and in the data sheet, see that this microcontroller has kind of matrix. So any of the pins could be used for anything. Problem with this microcontroller, why I don't use it, why I wouldn't want it, is that requirement 3.3 volts and the pins are not 1.8 volt or 5 volt compatible, only 3.3 volts. But the purpose of having written crystal oscillator bus, pin direction, pin out, pin inputs, so they have kind of a pin multiplexer. Kind of. So there are several issues with this one. Here, when you see at all it can do, sure, it can multiplex pins, it has 8 cores, but it has no hardware support for UART and things like that. So you need to program it in the cores themselves. And I want hardware decoding for UART and SPI, because it's fast and it's reliable. Software decoding, even if protocols are simple, can make some mistakes. Hardware support. Parallax propeller, here we see that it supports video generation, okay, but it doesn't support the classical peripherals. Only software peripherals. Software basis interface. So what's important here is there are things where you can configure which on the core does what on the other pin. And what I've discovered is that there's another microcontroller which allows you to do that, and these are the PSOCs. PSOC 5. The advantage of the PSOC is that it's a bit more than microcontroller. So they put it on the microcontroller, they've named it PSOC, and it's the PSOC programmable system on chip, because there's really more in a chip. And what is good is, let's take the PSOC 5. PSOC 5, low power. Advantage it have is here. Vessel block, okay, that's not what I want. Yeah, programmable routing and interconnect, configurable analog blocks and digital blocks. Programmable routing. This is what I wanted. And you see it in the graphic here. You have all the ports connected to a programmable routing. So this PSOC is a combination of a microcontroller with, and this device shows it more. It's a microcontroller, it's a chip which has a microcontroller, it has an AD, it has EEPROM, it has a PLD also inside. So there's a PLD implemented in the SOC which you can program. this allows you to do programmable routing and interconnect. And that's exactly what we want. And the advantage of this PSOC products runs a Cortex M3. I don't remember which one I took there. Pretty much all the same. What's the difference? Blocks, universal blocks, they all have, at least the PSOC 5, all have USB. I have, so let's have 5,000 chips. Let's have a look at this chip sheet. So now they were made by Cypress. Cypress has been bought off, partnered with Infineon. Why there's Infineon branding, and here what you can see, digital peripheral. So versatile I/O system. It has on purposes digital peripheral programmable clock. And where is it written? That's programmable blocks, analog peripheral, and it allows you to connect any pins to anything else. And the advantage of this one here, voltage range, 1.7 volts to 5.5 volts, exactly the voltage range I want. And the advantage of this one also is that it has 6 power domains. So you could have one set of pins at 5.5 volts, a complete different set of pins at 3.3 volts, or one set of pins at 1.5 volts and the other one at 3.3 volts. And because it can do multiplexing, it's ideal for what we want. It can do matrix switching, and you can program analog multiplexers inside. So I could use this chip just programmable. I could use this chip just for multiplexing. I could use this chip just for using it in multiplexer, and I could have somehow program it over serial that it does multiplexing and which pin goes to what, because it also is capable of doing analog multiplexer. But this, so let's have a look at the chips. The problem is the chips are really expensive, Cypress, and I've never worked with them. I've worked with a lot of microcontrollers, well, with a couple of microcontrollers, PIC, AVR, that's Mega, I've SAMD, SAME, PIC 12, PIC 16, PIC 8 also. Worked on what else? I didn't work a lot. I did write some code for the parallax once, but it uses a spin interpreted language, or its proprietary language, spin. I think they now have also a C compiler, but when I did it, it wasn't spin. So I did a tiny bit of parallax. I did some MSP, some ESP, but I've never worked with Cypress, and I know why. Because really expensive. We look for this chip. One of the chips costs 20 euros, while I could have other microcontrollers which cost only 4 euros. So they're really, really expensive. But they exactly make what I do. And for example, if I would have to use the STM32, it's say 4 euros or 7 euros, I don't remember. Then we have 5 analog multiplexer, 2 level shifter, 3 shift registers. This makes more than 20 euros. So in the end, this chip costs less if I combine everything in one. So I wanted to try it out, and so also it was, I did everything, all my code is on the STM32, but I don't think it is important to choose to be stuck on a microcontroller. The microcontroller, I just use it because I'm very familiar with it, and if I want to develop some code, I have some cheap development board I can throw away, and I'm very familiar with the thing. I already have code running. This is why I used it. But you shouldn't be stuck on that. And I have no problem switching microcontroller if it fits perfectly the purpose. And in this case, this seems to like fit the purpose. So there are several microcontrollers. This is used in apps called Cortex M3. This is the PSOC 5. There is also a PSOC 4. Let's look at their. So we don't need this way. This. Now let's go to products. So they have other PSOCs. Finest one. Have PSOC 4. The PSOC 4 uses an ARM Cortex M3. And the problem that's so I had to figure this out because I wasn't familiar at all with the PSOC family. I want to have an analog multiplexer, programmable analog block. That's good. And I want to have programmable digital block. This allows me to multiplex quite well. So only this family or this family goes into play. The lower family are less expensive. This is the PSOC 4100 family. And since I'm already programming with another microcontroller, I also want to connect it over USB. I could have it connected. I could have one microcontroller talk serial to it and then have the result over serial. But if I'm already learning about a microcontroller, why not take one which also does USB? I don't need a second micro USB interface. And on the PSOC 4, only the PSOC 4200 has 200L, the L series has USB. They also have 1.7 volt to 5.5 volts. Take just any data sheet there. They have an issue, is that so they're less expensive. Let's have a look. They so they have also programmable multiplexing. We want programmable analog, programmable digital. That's what we want. Now embedded micro. We want stock for L series live filter. They're already less expensive. The big one is 10 euros, and look at small quantity. We have one for 6 euros. So they're currently not available because there's an IC shortage, but we could find them. So this is less expensive. The issue with the PSOC 4200 is that it doesn't have multiple domains. It is kind of an issue. So it is not written here, and if you look at the IO, VDDIO, there's only one VDDIO. Yeah, we don't see VDDIO1, VDDIO2, and so on. So all the pins would have to be at a specific voltage. Now, I might switch. We could use the PSOC 5 because we don't need to interface with 3.3 volt anymore. We just want one programmer. We just want one programmer, something like this, which interfaces to the target, and there will be only one target voltage. So we could actually use this PSOC, and I'm not sure if I'll do this or the other one. That's still in my head. But that's the PSOC 4200. There's another PSOC family which does approximately all the thing which the PSOC 5 does. PSOC family. This is oh, is it not here? Here, 8 bits. And JavaScript isn't working. Okay, we have the PSOC3 products. And they do exactly what's also programmable PLD, and they have also routing for analog and for digital. It's almost exactly the same picture as the PSOC 5. Look at this picture, look at this picture. Oh, it's the same picture. So it's just that the core is different. For PSOC 5, we have a 32-bit ARM controller, and for PSOC 3, we have this, I think it is free now, this 8051 core. One is a core. Chip developed. I don't know why a lot of very, very low-end chips use this, because I think it is free to use. It is free to implement. And it's also, that's probably also why this PSOC 3 is a lot cheaper. If we look at these, go back, look, have a look at the one in quantity. We can first one at 2 euros, and they do the same thing. Almost the same thing. It's just that they have an 8-bit microcontroller instead of a 30-bit microcontroller. Since I'm not doing a lot of number crunching, I might also use this one. So I don't know exactly. We're using a PSOC 5, which is full features. Where I use a PSOC 4 because it's still 32-bit, so it's kind of a bit faster and more powerful, and still sufficient because it provides connect. Or will I use a PSOC? I don't know yet which one I will use, but the PSOC family leaks seem nice. And what I got to try out is this device here. This is, so whenever I try a new microcontroller, I always get the development board from the manufacturer. And this, how is it called? Yeah, no, that's, I think, here. CYCK kit 05059 PSOC. And I tried this one because it was, I think it's $15 for this development board. And what's very good is that it has one of the PSOC which costs 20 euros now, and the development board costs even less than the 20 euros. But the most important part is they have a lot of examples, they have good schematics, so we know that this board is really working well. And it comes with a programmer, so there's even a second PSOC 5 right here. In this case, it is used to program this one, but you could break it apart and use this also as a piece of programmer. So ideal development environments. And I have to say that the quality is quite good. I've looked at the data sheet, I looked at the schematics, and it is well described. So this is what I did last week. I've ordered a PSOC kit, development kit, and I've tried it. And let's try it out to see if it does what it wants. The issue with PSOC and a hard not letdown, but a hard negative point is that the development environment is called PSOC Creator, and it is only meant for Windows. And that's kind of a pain. So let me. So I do have Windows virtual machines, and to try out, why not? I've also tried to run it on the Linux. We're using Wine. I'm able to install it, and I'm not able to compile the code for it. Well, to generate the code for it, because you have to remember that this is kind of a CPLD, FPGA, and tons of things together. So PSOC Creator, this is the yeah, license expiring. This is an image for test the browser, so that they are time limited. And no, this is not the password. So this is the piece of creator. It's for now only works on Windows. So it has two parts. You need it because it's not only code. It does generate, it has an FPGA and it has PLD routing inside. So it has to generate very low code which gets flashed onto the device. This doesn't work, although installing the software on Linux works, this generation doesn't work on the Linux. The other thing it uses ARM GCC, which is available on the Linux. So I think the design needs to be done. So yeah, the design needs to be done on the Windows, but once the design is done, all the coding can be done on the Linux. I hope this is this way, because I don't want to spend all my time on Windows. This is a huge negative point, but else I'm starting to like it. I've only played 1 week with it, and I was able to have a demo and to try out if this works. So for example, here we have 2 pins, which are called A0 and A1. We want 16 pins, but this is just a demo. What we want to do is at one point we want to measure the voltage. For that, I use the analog multiplexer. So this allows me to select which one I want to measure, and then I measure it using the delta sigma analog to digital converter. And the same pins are also connected to a UART interface. And again, these are not analog multiplexers, but digital multiplexer. I can control them using a register, and I can choose the TX on which of the 2 pins it goes, and same thing on RX, which on the 2 pins it goes. So this part looks really like a schematic, and what it's doing in the backend is writing VHDL code and programming the PLD. I don't know, I probably can have a look at the VHDL. I've never programmed an FPGA, so I'm really not familiar with this domain. But once you have drawn your schematic, you can compile it, and then it generated the source. So for example, for the delta sigma, it generated some code. You have the header, you have the C code, and code quality is quite good. We look at the interface, look at delta sigma. You see that the documentation is okay. Start, stop is fine. What you have to do also, what is important for the blocks, so they have plenty of blocks for routing, plenty of other stuff, and can configure everything here. You don't have yourself to know all of the registers because most of the thing can be done here. There's still a technical reference manual, but I've never opened it yet. I somehow didn't have the... And if you look at kind of this data sheet for this component, it tells you what it does, it tells you how to connect it, it tells you what the methods are and how it works generally. And then once it's configured, it generates the code. The code has good defined headers. And I'm not really used also to work with IDEs. I don't know, not sure if you looked previously. My IDE is a text editor, Vim. It's also in a terminal. And then I do everything with makefiles. So I don't work at all with IDE. Well, although sometimes I do have to work with the Arduino IDE, and I found it very clumsy. Be better, but at least it works. I started programming with Eclipse. I didn't touch Eclipse in 10 years, I think. So I had to use this IDE because you have to program the device using it is a bit different because you also program all the clock yourself, like you would. You have to program on which pin goes. So here, for example, the A0 signal, I've mapped it on this pin, but you can map it on any other pin. It will do the routing for that. And then I wrote code demo code to figure out, and see that the examples are also very good. And based on the examples, all these projects here are examples for the different part. For example, this is UART. Here I learned about UART. Here I learned how to use the delta sigma converter. Here I learned how to use USB UARTs, and with that I was able to program this chip. So let's connect it and see what it does. So it is programmed. This is the code, and if you don't believe, you can reprogram it. Programming, flashing, standard procedure. Device was successfully programmed and from this code. And now disconnected. Have another smaller thing. Journal control. So we can see what is happening if I connect device. This is over USB. I already changed the product name, and it is recognized as ACM. Connect to it using ACM. If I press 0, it measures the voltage on channel 0. If I press 1, it uses the analog multiplexer to measure the voltage on channel 1. And see that the measuring voltage works quite well. It also reads the digital pin. This is what we see here. And this is below the 2.2 volt threshold, so it is considered as a 0. This is above, this is considered as a 1. And this is a digital readout. So we already have analog readout, digital readout, and I wanted to have up. Now we have the other part, the UART part, US 0. And now if I press on T, it sends X, Y, Z. This is what you see here. So on the same pins, I'll show you afterwards, on the same pins it was able to send, oh, maybe I try to show you my setup. Go that far. Very stable. I am. Stop it. Okay. Focus. Bit. Focus. And here. These are the two pins I've connected, and these two pins are also connected to the USB to UART converter, which is there. Which is right here. That's the USB to UART converter. This is why I have two terminals. And for example, if I press R on this one and I send T, get it receives T, R, and I send D, it receives T. And this, all the things have been done on these two pins. So we have TX, RX, ADC, and digital input and output. And I was able to do that IDE in a week. So that's the update. So for the IOVoodoo, we will definitely use a PSOC device because it does exactly what I want. It multiplexes all the digital and analog domain. I don't know which one I will use it. We will use the 5 because I've written code for the 5 and it works. And I could even have a complete demo because I can break this part out. The other camera again. Better look. Yeah, you can break this part out, and this part you can. It's also written it's also defined in the schematic which one of the resistors you have to remove on the other side. For example, here there is a 0 ohm resistor. This is just a link. You could remove this one. It's not exactly this one. I think they're on the back. You can disconnect the VDD, the voltage target, to the VDD. So you could provide the other voltage. And this, using this board, I could actually implement the complete IOVoodoo and figure out if it works. I don't need any external parts like the analog multiplexer or the shift register or the level shifter. Everything is compatible. Everything is on this board. So the question, what I didn't decide now is, will I use a PSOC 5 because the whole code will be there? Will I use the PSOC 4, which is a tiny bit cheaper and powerful enough, and I only need to have one power domain? Or will I use the PSOC 3, which is as powerful as the PSOC 5, has multiple power domains, but just has a smaller CPU core, as an 8051 instead of an 32-bit ARM Cortex M3. Now I didn't decide it. It probably will be depending on the prices of the devices and on the availability of the parts. But yeah, I have to say that this was the opportunity to test another microcontroller, and I'm completely fine with completely switching analog microcontroller and have the code ported to this platform. I still have to figure out how to do that. I'm really not fond of having to use Windows for writing the code. Probably I just have to use Windows to generate one time this schematic. Once this is generated and all the source code has been generated, which I need, I kind of think I'm able to compile everything under Linux and then use ARM GCC and make files. So if it's just about improving the software without touching at the schematic, it might still work on the Linux. I have to try it out though. That's then a compromise to make. But I would be able to make this having Windows for circuit parts and Linux for the source. Yeah. And the last part I wanted to talk about is, yes, I also had a look. So while looking for microcontrollers which are able to also have this kind of I/O multiplexing of I/O routing, landed on the one which everyone talks about currently, which is hyped probably much. This RP2040, which is the ARM Cortex M0 microcontroller from Raspberry Pi, which is not expensive and also a bit powerful. Let's have a look at the data sheet. And the problem with this one, colophone. Colophone. Yeah, RP2040. That's weird to have a data sheet where the first page doesn't tell what the device is capable of. Go to production. So here, yeah, the problem I have with this one. Let's have a look. So it has here, programmable LDO to generate clock voltage. That's okay. It has PIOs which can be configured. This one, why is it PIO machine? Okay. So on the PSOC, you have to use resources to generate UART and SPI clocks. They use their form data block, UE. They use kind of resources. So the PSOC will probably not be able to have 3 UARTs, 4 SPI, and so on, and 2 I2C, which an STM32 would provide, and then tons of timers, which are baked in the chip. But I don't need all of them. I need one microcontroller, I need one UART, one SPI. Probably I could also program one of these block to do JTAG or SVG if I don't repurpose SPI. I would have one timer to measure the frequency, but I think that's pretty sufficient. The 24 blocks inside here are pretty sufficient. So, but if you want like 8 UARTs, I'm not sure that this is good enough and it has enough resources. I don't know, because if we have a look here, for this simple schematic, if we have a resource meter, I'm using 14% of the, these are the blocks for digital, for doing things like this and probably like this, I don't. And yeah, we're already using 14%. So it's fine for, if we want 8 of them, that wouldn't be possible. We would have to use, but for all needs, it's good enough. Now, this one, programmable, where is it written that this has a dual core with why I would dual core probably use core. I don't programmable IO peripherals. I know that's the other thing. Function here. This is where it's written. IO peripherals, and you can select on, so you can select on which GPIO the UART peripherals go. So this is also what we want. The problem is you cannot do the same thing for the analog domain. You can have only 4 of the pins can be used for the analog domain. Where is it written? Here. The ADC could only be measured on one of these. So that's already a no, because we want to be able to measure on 16. Else, again, I would have to use an external multiplexer just for the analog part and still be able to use all the other pins for the digital parts. That would also be a choice. The problem is here the voltage, IO voltage, only 1.8 volt to 3.3, and this is only where we come to limitation. Yes, there are not a lot of devices which have 5 volt, but I wanted 5 volt support. This microcontroller does not support 5 volts. So no, I don't try to convince me that the new RP2040 is a messiah and can solve all my problems. It doesn't fit the things I want. I cannot do analog on all the channels, and even if I would have an external multiplexer, one, which is not a lot, I cannot do 5.5 volt IOs, which I want to do. Someone else. Else, I think it's pretty nice because it's cheap. It can really do the multiplexing we want. And if I would have to do it only with 3.3 volts, I would be fine with this one analog multiplexer. And there we have it then, 3.5 volts. So the question is now, yeah, one of the PSOC families. I don't know if PSOC 5, PSOC 4, or PSOC, I don't know. But I wanted to have an update and just show you that complete design we had in the beginning, this design with the STM32 gets completely off board just because there's a microcontroller probably does the job a tiny bit better for the needs we have, and that for any project you have, don't be stuck to a microcontroller just because you are familiar with it. Be curious and test other microcontrollers. And that's all for today. I wanted to make an update about the hardware design. This is how hardware design is. Sometimes you have to, and sometimes you have to throw everything overboard which you decided previously. But you can follow the hardware design, so it's not too long. 1 hour condensed after one. I've condensed all the choices after 1 week of work. And I think that's it for today. What I will try to do though is, I have an issue So I'll do it like so. This is the end of the stream. I still want to try one thing on this just for fun. The main project is done. I have to do a lot of coding with the PSOC, and I will do a prototype of the SPC finder using this PSOC because it does everything I want. It's development board. So what I want to do now is that I want to try out if I can restart OBS without ending the stream, without ending the video stream, because it happens from time to time that I have glitches on the USB port and then the picture freezes like this. Now the picture is frozen. If I reconnect the HDMI grabber, it works again. So in theory, so now you don't see it, the image is frozen, but the USB capture card has been running again. So I want to test if I restart now OBS, will it end the stream or can I continue the stream if I do it fast enough? So I will try to restart OBS and see if the stream ends or not. If yes, then that's the end, and that's the end of it. No, then it's good for me. So let's start it. Bye bye if it doesn't work. Oh, stream has started again. Let's check out if this. Oh, okay. This is good. In Twitch, this didn't work. If I end the stream with OBS, the stream ends. And here, the stream doesn't end. It just gets stuck for a couple of seconds, but it still continues. I'm able to restart OBS. Very good. So YouTube has an advantage over Twitch. And also, so this is a Winkelkatze. I've learned about it when I did some work. So just telling stories about my life. This is a Winkelkatze. This is very useful when you do recording or camera work, because very often you set up the streams, you set up the camera, but you don't know if this is a static picture or not. Sometimes you have clocks, and if you see clocks moving, you know that the camera isn't frozen. Like, for example, we did when the capture card has an issue. So what people did, and with people I meant the C3VOC. The C3VOC is the Computer Chaos Congress. So that's C3 and VOC, Video Operation Center. So the people doing the recordings and retransmission for lots of CCC events and for other events. And I worked with them from time to time, and I did some recording from some of the events. And this is where I learned about the Winkelkatze. This is also their mascot. VOC. That's website. They have very often find this logo. Voctomix, this is the software they use for mixing everything. So they have very good software for conference. See? For conference. I don't have any pictures of VOC. But this Winkelkatze, and it's a very good idea. It shows you immediately if something is stuck or not, if the fixed image or if your recording setup works. Images. So here, one of these cats. Yeah, that's the. Ah, here, see the logo also. On the left, there was some animation. If nothing was happening, then yeah, Octocat. Ah, that's how it's meant. The Octocat logo. So the Winkelkatze, which was just there to debug the stream, has become their logo, and now it's called Voc. Now the kind of official logo is the Octocat. That's nice. But yeah, so I tested YouTube stream, works it better, and I can start the stream. with tweezers. But that's it for today. I've explained the progress. I will have to work on the microcontroller and implement my SVG finder on this new SOC, put it in a board, and I think it will only be on a breadboard, and I will not make a prototype board like this. I will, well, like inside here with all the connections, because I don't need other parts here. I don't need the level shifters like here. The level shifters are already inside. I just need. And once this is done, then we can restart the hardware design. So all the work we did with creating the parts in the part 2 is for nothing, because we won't use the parts, but at least you've learned how I design my parts and my libraries, and I won't show it again. I will do probably the same with these parts and be able to do that. And for example, if I'm good enough, I couldn't put everything not in a big board like this, but everything could fit in a board like this. So let's see. But for now, the stream is ended, and I'll tell you if I progress. And while you probably see some streams where I'm testing other things or building other things. But okay, let's end the stream. So see you and enjoy.